Okay, so then now the live stream is working. Okay, I think now we can start. Okay. So good afternoon, everyone. Welcome to the first Rocky Award discussion for this year. And I hope we continue lots of great discussion from the past year. And just a short announcement for the audience. Please use your full name for the name. And please keep muted through the talk. And when you speak, please turn on your video if possible. Okay, then it is my pleasure to introduce Dr. Hannah Diamond-Lowe, speaker for today. Hannah is a senior researcher at the National Space Institute, Technical University of Denmark, DTU Space. And she is going to introduce us the observation of Rocky Exoplanets, the populations, atmospheres, and the open questions. So, Hannah, please.
All righty. Thank you so much. So I'm just going to share my screen. All righty. Hopefully you can all see that. Yes. Okay. Great. Well, thank you for the lovely introduction, and thank you for inviting me to speak at this virtual discussion. So as said, I'll be talking about the observations behind observing rocky exoplanets. I'll start talking a bit about their populations, get into their atmospheres and what we've done already, and then push into some of the open questions that I think we'll be able to address within the next year and then maybe going forward into the upcoming years. So let's start with exoplanet populations. So what have we detected? What do we know? Where are the rocky planets? And this is a diagram of all of the planets we have detected so far. This diagram's like a year old, so there's a few more points on here, but it's basically the same. So on the y-axis, we have these planets by mass, and their masses in Jupiter masses, as a function of their separation from their host stars. So I've also, for context, put our solar system planets on this figure. So you can see Jupiter right at 1 Jupiter mass, pretty far, about 5-6 AU out from the sun. You have the Earth at 1 AU. 1 astronomical unit is defined by the distance from the Earth to the sun. So this makes sense here. And when you sort of look at this, and sort of take a step back and take a broad view, it does look like that we have not, that we don't have very many exoplanets in the same parameter space where we have solar system planets. We don't think that's because the solar system planets are particularly special or different. It's mostly just a detection bias. So it is harder to detect planets that are farther from their host stars. And it is also harder to detect smaller planets. So if we care about planets down here in the parameter space of Earth and Venus, we really need to push our detection down towards these smaller planets. Now, I want to introduce a little bit just how we make these detections, because it comes into how we understand planets, and particularly the small planets we're interested in. So the two main discovery methods that we use for terrestrial exoplanets are the transit method and the radial velocity method. Now, these both are discovery methods, but they also tell us key pieces of information about small planets. So let's start with the transit method. This is a really nice graphic, which I'm crediting here to Alyssa Obertas. So this is a sort of toy diagram of a transiting exoplanet. So this is a planet that orbits its star and passes in front of its host star from our perspective. So that basic geometry gives us a transit depth, which is very simply just the ratio of the planet's projected area over the star's projected area. And the data we get looks very much like this. So you're sort of monitoring this star. It has some light that you're detecting. And then when the planet passes in front of the star, you get this dip. And from this dip, you can directly read off one, that the planet's there. If you see this multiple times, that's a detection. But you can also directly read off the planet's radius relative to the star's radius. If you know the star's radius, then you know the planet radius. And why I really like this diagram a lot is because this in theory looks very nice, and wow, what a nice big signal. But we have zero spatial information about this system. And this is actually a much more realistic depiction of what we actually see. So the star, the whole system is just this one pixel, and we monitor it, and it will dim and then it will brighten again. And sometimes it can be spread out over a couple more pixels, but you're not resolving any kind of stellar surface here. This is a good example of what the TESS pixels look like. So TESS is the Transiting Exoplanet Survey Satellite. It is a broadband photometric telescope. It is currently operating. It has found an incredible number of planets via the transit method. And why TESS is so powerful and why it is the great successor to Kepler, the previous telescope that used this method to look for planets, is because it's one big photometry bucket. So it's one big bucket and all your photons go in there, and you can just collect as many as you can, and then you can look for these signals even around relatively faint stars, or even if these signals are pretty small. Now, the complementary method to this is the radial velocity method. And from this, you can get a mass. And the way this works is that same planet that's orbiting its host star actually induces a small gravitational pull on the host star. This is sometimes called the wobble method. And the way you detect this is to take a spectrograph. So now you don't have one big light bucket. You actually have to spread your light over and try to get its constituent wavelengths. And then we know the rest wavelength of specific molecules, and we can see those molecules in the stellar spectrum. And as the star wobbles a little bit back and forth due to the pull of the planet, you see this stellar spectrum move a little bit, and that's being illustrated down here. Now, this method is very powerful because it can get you a planet mass, and it can even do this for planets which do not transit, so that's exciting. But it's limited in that it can only do this for bright targets and nearby targets, and targets where the planet is massive enough to make this wobble noticeable. And that's because you don't have this big light bucket where you just get to put all your photons. You have to spread all those photons out, and so you need a lot more of them. So these two methods together, when you can do both of them, becomes very powerful, because when you have a radius and you have a mass, well, then you can get a radius mass diagram, but then you can get a density. And this is giving you a bulk picture of what that planet looks like as a whole, not just its size, not just its mass, but what might be going on inside. So this is a figure, a radius mass diagram, as we say. So radius is here now in Earth radii as a function of mass in Earth masses. And if you're a planet that has made it onto this graph, onto this figure, that means you have a measured radius and mass, and I've made some cutoff in precision so we don't have huge error bars everywhere. And if you were just to glance at this, you might think that gas giant planets are the most common planets in the galaxy, and this is again a detection bias. Remember, it's much easier to detect larger planets. That's because they make larger transit signals. They also induce a larger pull on their host stars. So to kind of help with this, I've put a histogram here that's just the radii. So this could be like mostly just Kepler and some TESS planets, and it's a little bit more of a statistical picture. So hot Jupiter planets, these are the Jupiters, the gas giants that orbit close to their host stars. We found a lot of them, we've studied them a lot, but they actually make up about 1% of planets in our galaxy. Much more common are these smaller planets. And there's actually kind of two flavors they come in. One are these terrestrial planets. These look a lot more like Earth and Venus, which we're familiar with. And then there's these sort of sub-Neptunes, which are sort of the size and mass of Uranus and Neptune, but they orbit much closer to their host stars, so the name is not perfect. But this is a rocky world discussion, so we're going to start zooming in towards our terrestrial planets, but I want to first make a little bit more comment about the terrestrial planets as they relate to the sub-Neptune. So I'm going to zoom in on this dashed box I've made here. So this is just zoomed in. We still have radius versus mass, and I've drawn these kind of composition curves, these like isocomposition curves. So Earth's composition is right here on this orange line. Here we have Earth, here we have Venus. And then as you add more volatile material, more water, more gas, the planets kind of start to move off of these rockier compositions. They might have some large amount of water, they might have some hydrogen envelopes, and then you get these kind of different populations. So without knowing much more than a radius and mass, we can make these sort of two big separations in the population. And just to give a brief history lesson, this population used to be divided based on radius. That's because the Kepler mission, which I'm showing a little picture of Kepler here. Kepler was this great statistical mission. It pointed at one patch of the sky, stared at it for 4 years, and is really a statistical sample of planets with some detection cutoffs that are well known. And what Kepler found, so this is a histogram of sort of number of planets as a function of size. So here again, giant planets, actually very uncommon. But there's actually this natural sort of bimodal distribution that comes out. And it was thought that, okay, we have super Earths on one side, these mysterious sub-Neptune planets on the other. And this division has still held, but we can now with tests finding planets closer by to us, we can actually go and get masses in addition to radii. And so to sort of add an axis to this, going back to our radius versus mass, there might be a more natural cut to make, not just on radius, but also on density or on bulk composition. So there is this paper from last year, a couple years ago, that was sort of positing that maybe instead of the radius valley, you have this sort of density valley. So this would be, here we have our Earth-like composition, and then separated, we have this sort of 50% water or some volatile composition. I think this is very compelling. It's still relatively small number of statistics. These are only the planets with very, very high precision measurements for radius and mass, but it's definitely a direction we're kind of going in. And this is sort of where, I mean, we could do this for more planets, but we're going to be a bit stuck here if we only keep going after radii and masses. And that's because even though, at some point, even if you shrink these error bars a little bit, you don't know how this bulk composition is actually distributed within the planet. Is there an atmosphere? Is there a large ocean? Is there water in the mantle? We won't get those answers just from a mass and radius. So we need to go beyond and look at exoplanet atmospheres. So kind of getting into some of the exciting work that's been done for rocky planets, we need to there's sort of three main methods that we use to try to probe the atmospheres of these worlds. One, and this is very not to scale cartoon diagram. So one is the transit method. So as the planet goes in front of the star, a little bit of light can filter through a planet's atmosphere on its way to our telescopes. And based on how much light is blocked or can pass through, we can get what we call a sort of spectral fingerprint. And we can say, oh, maybe there's water in that atmosphere, maybe there's methane. We can run a bunch of analyses. The other option is you can actually watch as the planet passes behind its host star. And if you look at this at redder wavelengths into the infrared, you can actually start to differentiate thermal emission that's coming from the surface of the planet relative to, of course, the thermal emission you're getting from the star. And I'm going to talk actually quite a bit about this method, but we'll get a little bit more into it. There's also the phase curve, which is, as it says, you just watch the planet all the way around, and there's a wealth of information you can get from this. It's also very time intensive because you have to wait, you have to watch as the planet goes its whole orbit. So what are some big results? Well, as of today, we have so far not definitively detected an atmosphere on a rocky planet. And I've put on this graph all the rocky worlds that are pretty much close enough that we can do atmospheric follow-up. I think I've got all of them. I might be missing one or two recent ones that came out in the last month. But I've arranged them by the transmission spectroscopy metric, which is just a sort of rough way to say, well, planets higher up on this graph, it might be easier to observe their atmospheres, planets lower down or harder. And there's also a correlation, so how far these planets are from us. So out to about 30 parsecs, it's getting pretty tough to look at the atmospheres of these guys, but it might be possible. I will say, these are the color of the points is the equilibrium temperature of the planet. So a kind of rough estimate of what this planet's temperature might be. The talk program for extreme solar systems just came out, so I think I might be changing this slide soon, but hopefully. But there's nothing, I will say nothing published as of today has definitively given Rocky exoplanet atmosphere detection. Okay, but so what have we been doing? If have we not tried? Well, no, we've tried a lot. And this is kind of where we were at the launch of James Webb. The only atmospheres we could really address for terrestrial planets are if they have a little bit of hydrogen and helium that can puff up an atmosphere enough where it's detectable with things like Hubble or large ground-based telescopes. And all the planets I've put little X's over here. These are all planets where we've definitively said, okay, there's no there's no even a little bit of hydrogen helium in these atmospheres. So it's like a little boring, but that does mean they might still have atmospheres that look something like Earth and Venus. So I like to, there's more discovery space there. And we are starting to dig into it now with James Webb. So we know now that some rocky planets we think have basically no atmospheres at all. They're for all intents and purposes barren rocks. So this was the first example of this to come out. This is the terrestrial exoplanet TRAPPIST-1b. You may have heard of the TRAPPIST-1 system. It has 7 terrestrial exoplanets orbiting a very small M-dwarf star. These were observations taken in secondary eclipse. So I've made a little key up here. If you're like, which part of the orbit? This is kind of how you're going to know. So this is secondary eclipse with James Webb with the MIRI infrared instrument. And you can see here what a tiny signal is being used to make this detection. So this is a very shallow depth, only about 1,000 parts per million. That's like 0.1%. That's very small. And the results is that they were able to put this one data point from 15 microns. So we're going, kind of going back to the light bucket here. This is not a spectrum. This is just a kind of bucket around 15 microns. This bar shows sort of how the width of that bandpass in wavelength space. And they were able to compare this flux measurement at 15 microns to some models. So there are these black body models, which are this blue and this green line at around 500 Kelvin. Then there's a much cooler black body model at 400 Kelvin. And then there's some models here that actually include molecules like carbon dioxide, and then a little bit of, or less carbon dioxide plus some ozone. And the point is they're saying that, well, this point is a deeper eclipse than we would have seen if there had been some atmosphere equilibrating the temperature of the planet, moving energy from the star around the planet, or if there had been an atmosphere that actually has some carbon dioxide. Okay, so let's dig into that a tiny bit more because it's a little complicated. So this is the power of secondary eclipses and why we want to look at them. So let's go to the theory behind this. This is from a paper by Daniel Cole, who's done a lot of work in this space. So for planets that are tidally locked, you can make a calculation about how the planet to star flux ratio, so basically how much flux the planet puts out as a function of its orbit for different atmospheric cases. So for the dashed line, we have a bare rock, and then this is the surface pressure of 0.01 bars. That's a very that's a very light atmosphere, not much there. 1 bar, Earth's atmosphere has surface pressure of 1 bar, and then 100 bars, which is about what Venus has. So as you can see, these curves change a bit. These are 3 different planet kind of options. Here's TRAPPIST-1b, which I was just showing observations for, and these were 2 other terrestrial planets. And you can see there's a lot of information in these curves, but also if you just look at this 0.5 phase, this is when the planet passes behind its host star, there's quite a substantial difference between the bare rock or tenuous atmosphere case and the cases where there really is a substantial atmosphere. And then there's a little bit of wiggle room in between where maybe you have kind of a tenuous atmosphere, but it's not enough to really flatten this flux ratio. So this is sort of the crux of the argument. You're not learning any kind of spectral information necessarily, but you are saying whatever that atmosphere is made of, if there's enough of it, it will change how your planet to star flux ratio. It'll change your eclipse depth from this to this. So that's what we're looking for. That's what we're looking for here. So this was done again for TRAPPIST-1c this time, a tiny bit cooler. They got this very nice secondary eclipse, and this is their result. Now, the paper is demonstrating that this is not definitive evidence of a thick atmosphere, but as you can see, it could possibly be consistent with maybe a more tenuous atmosphere, and so there might be a little more work to do here. But the kind of message is that some of these rocky planets really do not have, when I say no atmosphere, like you can always conjure up a tiny little wisp of something, but these do not have substantial atmospheres that we would be able to detect. Now, there's also some cases that have proven a little more ambiguous. So this is GJ486b, another rocky planet. This is now in transmission, so planet going in front of the host star. And as you can see, you know, these models and the data are pretty close. But for example, this purple guy, methane, this is pretty discrepant with the data, you know, and the other ones to some degree. But what's really interesting is this water atmosphere actually fits the data pretty well, even better than the flat line. So is there water in this atmosphere? Well, the authors of this paper did a really nice job in being conservative with their results, and they did these higher level retrievals. And they found that they could explain their data both with a water atmosphere, so that's cool and exciting, but also this could be contamination from the star. When stars have cool enough spots, they can also produce water features in the spectrum. So this is ambiguous. We've seen other sources of contamination in transmission spectroscopy. This is, again, TRAPPIST-1b, but now in transmission. There were 2 transits of this object. And in the first one, when they include a star with a spotted surface, they got about 25% spots on the surface. And then one transit later, when they looked again, now they have 25% faculae. Those are hotter regions of the surface. So that's a little strange to have so many spots and then soon afterwards so many faculae. But the message here is that there is some noise being introduced by the star, which is an M dwarf, that is a bit problematic for looking at rocky exoplanets. So the big open question that I'm sort of posing here is, do rocky planets orbiting M dwarfs have atmospheres at all? And I've touched upon M dwarfs just briefly, but this is why we really care about M dwarfs at all, which is that every planet I've touched upon, every rocky planet I've touched upon in this talk, orbits an M dwarf host star. And there's a reason for that. It's called the M dwarf opportunity, which is just saying that a terrestrial planet orbiting an M dwarf gives you a much better chance of both detecting the planet and perhaps observing its atmosphere. This is because M dwarfs are small and they have lower mass. So that's good if you're looking for a transit or a radial velocity signal from a small planet. And there's also a lot of them. M dwarfs are actually our most common neighbor in the solar neighborhood. They're about 75%, I think, of stars nearby. As opposed to a sun-like star, which is much larger, much more massive, about five times larger and about 5 times more massive than an M dwarf. And so you're getting a much smaller relative signal from the planet. And there's also fewer of them. There's actually fewer targets. This is a much harder task. And actually, the Professor Lars Buchhe, who is a professor here, is trying to build a spectrograph to actually detect these planets. And it's not an easy task. So stay tuned for that in a few years. But M dwarfs are not just shrunken stars. And this is really where the problem is. So this is flux. This is sort of like normalized flux for a planet getting the same amount from 2 types of stars. And the black line is the quiet sun, and the red line is quiet GJ699, which is an M dwarf. And as you can see, as you would expect, the sun is much brighter. It's a hotter star. It's a bigger star. So, much more overall flux from the sun. But the M dwarf is brighter in the EUV. This is the extreme UV. And this is also part of the UV here. And why do we care about this? Why is that such a big difference? And it's because of this. So if you have a rocky planet atmosphere with some sort of solid surface, here's, some maybe little animals live on this surface, who knows? At the top of the atmosphere is where light from the star at high energy wavelengths is deposited. And these wavelengths are what drive photochemistry. So, production of clouds, production of new molecules, but it also drives atmospheric escape. And this is critical. If there is too much high energy XUV is X-ray and extreme UV, if there's too much of this high energy flux being deposited, it might actually strip away an atmosphere such that these planets cannot even support the sort of atmospheres we're trying to look for. So to figure out if this is happening or this is not happening, can there be atmospheres around M dwarfs? Are they too dangerous? This is kind of the big question. So one thing you can say is, well, let's scale up. So let's check for more rocky planets orbiting M dwarfs, see what the data tell us. So we know that these 2 TRAPPIST planets, probably airless or maybe a tenuous atmosphere. This guy is very hot, also proven to be a bare rock a couple years ago. But the way we're going to address this is I'm the proud PI of the Hot Rock Survey. So this is a large program that's going to do this emission photometry with 15 microns with James Webb observations for 9 new terrestrial targets. And if we've just started getting data, and we have a great international team where each target is being led by a grad student or postdoc You can use this QR code to learn more about those folks and what they're doing. So this is going to be, I think, the next step in answering this question. But remember, the M-dwarfs are also important. So we also have a companion program called Hot Rock Stars with HST that's going to gather UV information for some of these host stars. And what are we trying to do here? So I just want to talk quickly about the sample of planets we're looking at, since I'm sorry I don't have exciting new results for you. So the sample has 9 planets. So at the top here, I'm showing, this is again, radius versus mass. And we've chosen planets that are all within 1 to 2 sigma on this terrestrial composition curve. So crucially, they have both measured radii and measured masses. So we have a sense of their bulk composition going in, and now we're going to add this question of, do they have an atmosphere? But the stars are also important. So these planets span a range of orbital separations. Maybe you have to be a bit farther away from your host star. Maybe distance doesn't matter. And as a function of stellar radius, so larger stars typically brighter, but they have different properties in the extreme UV. These planets also have a range of installations, so how much flux they receive total from their host star, and also a range of surface gravities. And this is important because surface gravity plays a role in determining the scale height of a planet's atmosphere. So that's how extended the atmosphere is. And maybe if you're a planet with a higher surface gravity, it is possible that helps you hang on to an atmosphere, where a planet with a lower surface gravity might lose it. We don't know. These are all options. And of course, the planets range some equilibrium temperatures. So the kind of question that we're trying to answer is also going to give rise to more questions. So there's sort of 2 big categories that I can sort of for now anticipate coming out of this. And one is that irradial terrestrial planets around M-dwarfs have atmospheres. Maybe we find a bunch of atmospheres, and how exciting that would be. And then you can say, okay, well, what kind of atmospheres? We can start looking at transmission, trying to see, what chemicals might be lurking there. Trying to figure out how they got there. Are there surface processes going on? Is there evidence of volcanism? Any exciting kind of planetary science question you could imagine, we could be looking for. Then on the extreme other end of that, maybe irradiated terrestrial planets around M-dwarfs do not have atmospheres. And maybe that's a bit sad, but there's still a lot of there's actually in some ways even more exciting science that sometimes I'm like, oh, I hope they don't have atmospheres. But no, you can start learning about the surface compositions, which is a really exciting prospect. We don't know what the surfaces of any planet outside of the solar system look like. But if there's no atmosphere, you're kind of seeing right onto the surface. So you can kind of look for more scattered light at different wavelengths. This also means we kind of have a mandate to go after cooler planets around M-dwarfs. And this actually, there was a sort of slide deck floating about online preliminary results for this kind of 500 hours DDT time that's going to happen on James Webb. And this might be one of the targets of that effort. And it also means we might need to put more effort into looking for terrestrial targets around larger and less active stars. So G stars and also K dwarfs. K dwarfs are a bit bigger than M dwarfs, and that might be a sweet spot as well. So lots more work to do. So to wrap up here, and I hope I'm leaving a good chunk of time for discussion, if you've got nothing else, small exoplanets are the most common in the galaxy. They are everywhere. But we need sort of atmospheric information to really follow up and try to understand the differences between these small planets. So far, we have not published an atmosphere around a rocky world, because I really think this is coming in the next couple of months, but we'll see. But we are working on it. We're working on it for many targets. just because you find one doesn't mean you stop there. When thinking about exoplanet atmospheres, we have to remember to think about the host star and its high energy spectrum. It could be critically important to understand what is going on with an exoplanet's atmosphere or lack thereof. So we need to make sure we're thinking about these stars. And the big question that I'm excited about in the next couple years is do rocky planets around M dwarfs have atmospheres? If so, which ones? If not, why not? And then sort of towards the future, this is a stepping stone towards going after cooler planets, looking for planets around cooler stars. And eventually, we do want to be looking at terrestrial planets in the habitable zones of sun-like stars. We're not there yet, but this is the direction we are moving in. So I'll stop there. And discuss.
Yeah, thank you much. Thank you so much for very great summary and very stimulating talk. So to the audience, if you have any questions, please raise your hand on the Zoom button, or in the case if you don't have a mic, you can type in to the chat box. And while people are thinking about the question, I have kind of naive question related to the contamination from the star spots. So the typical lifetime of the sunspots are like a few weeks. So I would imagine that if we can observe the same system again after few weeks or a few months, we can actually distinguish whether the signal was contamination or not. But are there any such kind of general strategy for observers to observe the same system again, or is that a bit boring, the proposal?
No, that's a great idea, and people sort of talk about this. The problem we have is that we don't know the lifetime of spots on M dwarf. So there's through kind of long-term photometric monitoring of M dwarfs, some have a sort of, a kind of sinusoidal pattern suggesting there's rotation and some spots in some place and another, and that and you can see that sort of evolve over time. So those might be more long-lived, maybe less likely to get in your way. The TRAPPIST star in particular has proven challenging. It has an orbital period, that the star itself has an orbital period of about 3 days or so. So that's faster than the sun, and we have definitely seen like contamination induced by the star on a planet's transmission spectrum for one of the TRAPPIST planets. And then I think I even showed it, and then if I can go back here, I'm not sure that I can. Okay, I don't know why it's not working. From one transit to the next, and there's like consecutive transits, we're seeing a very different contamination pattern. So I think it would be absolutely great if we could just stare for a long time. And there is a James Webb program that's going to do this for about, I think it's like 40 or 50 hours. They're going to stare, might even be more, but they're going to stare at TRAPPIST and get like, and in that time, you'll get a bunch of transits. And so maybe you can start probing the surface of that star. But it's difficult to generalize this for all stars, for all M dwarfs, and then we simply don't have the observing time to do that kind of monitoring for every target. It's sort of, yeah. If we could do it from the ground, that would be great, but you're also limited because you can only observe at night. So yeah.
Thank you so much.
Yeah, great question.
There is one question in the chat box from Monica. Monica, do you want to speak up?
Hi. Hello, I'm Manika.
Hey.
Hannah, nice talk. So I have a question. Why host star high energy spectrum is important to study exoplanetary atmospheres?
Yeah, that's a good question. And that's also, I would say that's yeah, I'll tell you what I think is important. And I will also say that the only telescope we have that can really get the UV information from these M-dwarf hosts is Hubble. And the instruments on Hubble are working, but they're also kind of limping along. So we're very much in kind of just like just get the data and then figure it out later kind of phase. But why we think this is important to get is because we don't know, like, do these stars have atmospheres? Do they don't? We don't know yet, but we need to get the stellar information now while we can. So let's take the scenario where a terrestrial planet shows signs of an atmosphere, and we detect some molecules in there. The thing about that process is whether you're looking in transmission or emission, you're most sensitive to the upper atmospheres of the planet. You kind of think it sort of makes sense, right? Like if you're looking in transmission, you're getting more information, there's more light passing through the outer rings than the inner rings. And that you can sort of get more information about the upper layers. And so those layers are also the ones, if there is an atmosphere, that are most susceptible to photochemistry. So if you see some haze, if you see some molecule you don't expect, it might be explainable by photochemical pathways induced by the star. And this is especially important if, like, down the road you're ever interested in biosignatures. You want to make sure you know kind of where your molecules might be coming from. So getting that sort of UV part of the spectrum is important. If the planet doesn't have an atmosphere, you could say, well, did it ever have an atmosphere? Why doesn't it have an atmosphere? And if you have this even higher energy part of the spectrum, you can also make some calculations about atmospheric escape and mass loss. I will say there's quite a way to go. We can do very simple atmospheric escape with like hydrogen, but the sort of escape rates for heavier molecules are not well known. So I would say that's like an area of research we're going to have to figure out. But it will have it will be impacted for sure by the high energy flux. So even though we're not like I very much am trying to connect these two pieces like in sort of like active work, but they're a little bit far apart right now. And I would say I've mostly just been focusing on getting as much M-dwarf data as possible, get it while you can. So yeah, but that's kind of the theory behind why we care about this. Yeah.
So
yeah.
Thanks. And there is another question in the chat box from the Richard, and it seems he cannot speak up. I will read the text. So
I see. He's asking for the
yeah.
timetable.
Yeah, please.
Yeah, timetable of results for Hot Rock survey. Great question. As soon as possible. So yeah, I can be a little more detailed. The survey is actively going on. So we have to wait for the planets to go behind the stars, and then there's also just James Webb has its own scheduling timetable that you don't have a lot of control over. We have gathered, I think we got one more yesterday, so we have we have 5 now secondary eclipse observations. There will be a total of 22 by the end. I think the latest one won't happen until July or August. I don't have like results, but I can tell you that of 4 of those 5 observations, one just happened yesterday, but we do see the eclipse, so that's a good sign. We don't think we missed it. And so now people, members of our team are working really hard to analyze that data, try to clean it up, try to see what we're actually seeing. So as I said, there's a big conference coming up in March. We won't have results for that, but there's another Exoplanets 5, which is happening in Leiden this year. We're aiming to have at least preliminary results for most of our targets by then, with sort of papers trickling out kind of summertime. Yeah. And then it will take sort of some time after that to do. Of course we do an ensemble analysis as well. That will probably not be until the fall or a bit later. Yeah.
Yes, thanks. And there are two more questions. So first, Johanna, please.
Hi, Hannah. Lovely talk. Thank you. Can you hear me okay?
Yes.
So you talked a lot about all these exciting JWST observations, which is really like revolutionary in this parameter space. But I know that you've also worked on ground-based spectroscopy or spectrophotometry. And in particular, I was interested if you could just muse on what you think kind of the prospect is for rocky planet atmospheres with high resolution spectroscopy, kind of with a very future looking perspective.
Yeah. Nice to see you, Jemma. No, that's a really good question. So yeah. So what Joanna is referring to is I did a lot of work on terrestrial exoplanets from the ground using low resolution spectroscopy, and that was basically only being able to address these very puffy hydrogen helium cases, which would have been very surprising, but it's not surprising that we didn't find anything there. So we're basically at the limit of what we can do for low resolution spectroscopy. And when I say low resolution, it's like you're not really getting any, you're getting kind of broad features. When you turn up the resolution, you can actually start to distinguish individual molecular lines, and those will be shifted. So for example, if you're looking for water or carbon dioxide, those exist in Earth's atmosphere, of course. But for a planet, they might be shifted slightly such that you could retrieve them out of the data. And this is a very powerful technique that's been used for hot Jupiters. And we are currently pushing that technique with with some current large ground-based telescopes. We're pushing that technique for the sub-Neptune planets. It is hard. I'm involved in one of those projects, and they're doing a really good job, but it's really hard to pull that signal out. So the question is like, well, we're building these even bigger telescopes, these next generation giant segmented telescopes. Is that enough at high resolution to look at rocky exoplanets? And, you know, I really want to say like, yes, this is going to be super complementary and we're going to get all this information, but I am a bit worried only because it hasn't really been proven to work for sub-Neptunes, which have puffy atmospheres. And so I'm not sure what the next, you know, if it can't work for a sub-Neptune, it won't work for a terrestrial planet. I can try to muse on like, if these planets weren't around M dwarfs, maybe there's some room for like K dwarf rocky planet. You know, K dwarfs are much fewer spectral lines, so that would be easier. There may be like some of these really hot like lava planets. Maybe there's something interesting there. So these are really hot. They might have sort of like silicon vapor atmosphere type things. So something exotic like that, it might be good. I think yeah, I mean, it's really worth exploring. I don't see a clear path, but I don't think that means there isn't one. I think there's discovery space out there. I don't know. I think you'd agree with that, Joan. I don't know. What do you think?
Yeah, I agree. I was just interested in your thoughts.
Yeah. So.
Okay, next scene, go ahead.
Hello, this is Sean McClough, University of North Dakota. Thanks for the talk, Hannah. Similar question to what Johanna asked. With kind of the stakes, quote unquote, for looking at atmospheres around M-dwarf planets, and if the shift towards other stars, K-dwarfs and G-dwarfs, what your sense of the timing for that might look like, or what's needed to do that? Is that something that we can do with current facilities? It just needs a little bit more time to build up more signal, or is that going to require the next generation and the next generation kinds of telescopes?
Yeah, oof. Timelines are hard, right? Because it's like, oh, I'll finish this paper next week, and that never happens. But okay, certainly around G dwarfs, we do not have the capability for a sun-like star. We barely have the capability to detect. I mean, we do have a couple of rocky, small, no, I shouldn't say rocky because we don't know, small planets around G dwarfs. We have from the Kepler mission, that was a 4-year stare. And we got a couple, but not enough out to the habitable zone, right? So Kepler had the goal of determining the occurrence rates of habitable zone planets around G dwarfs, and it never reached that goal because stars actually ended up being a lot noisier than we thought based on the sun. The sun is like weirdly quiet. And then it didn't have enough time in its extended mission, RIP Kepler. But that's like just to detect that they exist. So we think they should exist, of course, but we don't know in what rates. And then to detect them close enough to make an atmosphere. I mean, we are very far from that ability right now. K-dwarfs may be a little better, but even so, you're looking at, you could do maybe sub-Neptunes around K-dwarfs, but a terrestrial planet around a K-dwarf, you're going down by another factor of 10 about in signal. And so even for James Webb, that's tough. And stacking a bunch of transits together, that's also tough. Just because you have to assume perfect noise properties, and we don't quite know those values yet. Yeah, that's kind of a bummer. But I think we're working towards, so one of the ideas for like the next generation telescope, which will be maybe not till the 2030s or even 40s, is this Habitable Worlds Observatory, which will try to look for terrestrial planets around sun-like stars, but it's going to use a method that I haven't touched upon here, which is direct imaging, and that is kind of the future. I think what we're gonna go to, which people have been saying for a while, but we really do, like, there's kind of no other way around it. So direct imaging is where you can kind of block out the light from your star, and that will allow you to sort of find planets that have been kind of in the shadow of that star or have been too washed out because the star is so bright. So that's like how you have to do it, a big survey of those, taking that to space. But yeah, I'd say we're a couple decades away. So let's get into our M-dwarf planets. That's,
yeah, sure.
Yeah.
And if I could ask a quick follow-up on that. So
Sure.
For something like the Habitable Worlds Observatory, the HWO, as it's sometimes I've heard it called.
Okay. Is it? Well, okay. I'll work on it.
Is there with we're looking at M-dwarf planets now, is there a sense that those future missions might be built, or the habitable worlds might be aimed more towards learning more about the M-dwarf rocky planets? I know direct imaging for those types of planets would be very difficult because they're so close, my understanding. Or is it really aiming towards those bigger stars and those wider targets?
Oh yeah, that's a good question. I mean, if the planet is at a wide enough separation from the star, I mean, masking out an M-dwarf should not be any different than masking out it should be easier, frankly, than masking out a sun-like star. Yeah, what you're referring to is if the planet's orbiting too close to its star, then what is it called? The inner working angle is such that you'll actually mask out the planet as well. So yeah, I mean, I think I also say too, like Habitable Worlds Observatory, it'll certainly find many cool things that are not terrestrial planets around sun-like stars. There might be sub-Neptunes. I don't see why you wouldn't go to other stars. I mean, the scope of the mission is not in stone by any means. So I think certainly there would be some effort to look at, not only sun-like stars, because as I said, there's actually not so many in our solar neighborhood. You're going to run out of targets. So including K dwarfs and even including M dwarfs, looking for longer period planets, I think that's extremely reasonable and would also be incredibly exciting. Maybe you can have habitable terrestrial planets around M dwarfs. You just have to find them far enough away. Yeah. And that actually, I will say that people might try to do with James Webb. So it is possible to do that. It's just hard because those planets are farther out. They're on longer orbits. It's harder to observe those. But that is something we definitely, definitely. I really think we will be trying that with James Webb, for sure.
Thank you.
Yeah.
All right. If there is no more question, we can stop here and wrap up the discussion. Thanks again, Hannah.
Yeah, thanks so much.
Thank you,
There
Hannah.
is- Thank you. And there is very short announcement for the next event. The next Rocky World discussion will be held on the March 7th, again from 1 p.m. UTC, and the talk will be given by the Sebastian Chano from IPGP. And the title and the abstract will be announced later on our email list as well as on our Discord server. So thanks everyone for attending, and see you in 1 month. Thanks. Have a good day. Bye.
Thank you, Hannah. It's really, really
Thanks.
interesting. Read it.
Great. Do I just leave now?
Everyone.
Yeah, it was a really great talk. Thank you very much.
Okay, yeah. Thank you guys.
Thank
Take
you.
care.
I'm going to end the meeting now, but take care.